All right, everybody, welcome back for another installment of QTM 200 Applied Regression Analysis. This week, we're going to be talking about how to interpret the multivariate regressions that we learned how to estimate last week. Now, as a general reminder, what we're hoping to do every class period is take some data that we receive from out in the world, and we hope to make an inference about that sample to a general population. And like I said, last week we learned about how to move from the bivariate case of having one covariate and one outcome to having multiple covariates and one outcome. And we talked specifically about the assumptions as well as the estimation procedure. Today, we're going to talk about how to actually interpret our multivariate regression in R. This is going to include a lot of null hypothesis testing, and specifically, we're going to talk about three different types of hypothesis tests that we can run. But before we do that, I want to briefly just go over what we talked about last week. So if you remember our equation for the regression line in our original notation that we used in the bivariate instance, we can index each of our outcome for each observation by yi. Then we again have just our first covariate and the relationship that we're interested in estimating, beta 1, where the regression line crosses 0 when x equals 0. And then we started talking about how to add on extra variables through the kth covariate. Importantly, we also then had our residuals or error terms for each observation. We also talked about how to represent this in matrix notation, where we have just our vector of y's. We then have our matrix of x's, the first column of which is just a whole column of ones. The second column is our first covariate. Our third column is our second covariate, and so forth. Then we have one vector, and that is the number of rows is equal to the number of betas that we're estimating, so the number of covariates that we have. And then we have our vector of residuals and errors. There are some also major assumptions that we are invoking in order to perform our regression, in the sense that we need these assumptions in order for the least squares, the summed squared residuals, to be the most efficient and unbiased estimator of that unknown parameter beta that we're interested in. The second assumption is that those errors are independently and identically distributed, and more specifically that they are normally distributed centered around mean 0, and they have a constant but unknown variance sigma squared. Again, this states that these are independent errors, like the error that I have on my observation is not dependent on maybe the error of another observation. They're normally distributed, and again, they have constant variance sigma squared. If these assumptions are met, then, like we said last week, we know that our construction of our estimate of beta, right, our x prime x inverse times x prime y, is the most unbiased and minimal variance estimator of the true underlying relationship beta. And we can then, because of that, perform these appropriate tests for these estimates. So we can perform t-test and f-test, which we'll talk about today. We can also then create confidence intervals for these population parameters, which also allows us to do hypothesis testing.